Salts. The word salt is another name for an ionic compound. And it's not an acid or a base, which means that salts have something other than hydrogen ions as their positive ion, and something other than hydroxide as their negative ion. And salts can be classified as neutral, basic, or acidic salts, depending on what happens to them when they dissolve in water. So when we look at salts that produce neutral solutions, we look at what the cation and the anion do in water. So a salt that consists of a cation of a strong base and an anion of a strong acid have no effect on the hydrogen ion concentration when dissolved in water. In other words, they're not going to affect the pH of the solution. The conjugate base of a strong acid or strong base have virtually no affinity for hydrogen ions, and they can't produce hydrogen ions. So as an example, if we look at sodium chloride, which is a salt, when we put it into water, the cation is sodium. Sodium is the cation of a strong base, therefore it has no affinity for hydroxide ions in solution. The anion is chloride, which is the conjugate base of hydrochloric acid, a strong acid, so the chloride has no affinity for the hydrogen ion. So sodium chloride is a neutral salt because it's not going to affect the pH of the solution. Let's look at salts that produce basic solutions. A weak acid has a conjugate base that has a significant affinity for protons. If you put salts of a weak base into water, it will take hydrogen ions from the water and it will leave hydroxide ions behind. A good example is acetate. So let's say that we have the salt sodium acetate and we put it into water. We know from our solubility rules that sodium acetate is soluble in water, so we're going to have sodium ions and acetate ions in the solution. Sodium is the cation of a strong base, so that will not affect the pH of the solution. But acetate ions are the conjugate base of a weak acid, so they have an affinity for hydrogen ions. So the acetate ions will react with water to produce acetic acid and hydroxide ions. And since hydroxide ions are being produced during this reaction, sodium acetate is considered to be a basic salt. So this reaction involves a base reacting with water to produce hydroxide ions and a conjugate acid. So let's say we want to calculate the pH of a 0.30 molar sodium fluoride solution. And it tells us that the value for Ka for hydrofluoric acid is 7.2 times 10 to the minus 4. All right, so our sodium fluoride is going to dissociate into sodium ions and fluoride ions. Now, sodium is the cation of a strong base, so it has no affinity for hydroxide ions. But fluoride is the conjugate base of a weak acid, so it is going to have an affinity for hydrogen ions. Our fluoride ions in the solution will react with water to produce hydrofluoric acid and hydroxide ions. Now, we're looking at a weak base solution, and they gave us the Ka for hydrofluoric acid. We're going to need the Kb value in order to do our problem. The relationship between Ka and Kb is as follows. Ka times Kb equals 1.0 times 10 to the minus 14. So we'll plug in 7.2 times 10 to the minus 4 for our Ka value, which was given, x for our Kb value, and 1.0 times 10 to the minus 14. So our Kb value will equal 1.39 times 10 to the minus 11. And we'll write our Kb expression. So we've got our hydrofluoric acid concentration times our hydroxide ion concentration over our fluoride ion concentration. Now we'll make an ice chart. We've got our fluoride ion, our hydrofluoric acid, and our hydroxide ion. We won't put water in our ice chart because we're not going to be dealing with it in our K value. So our initial concentration is 0.30 for our fluoride ion, because the sodium fluoride 100% dissociates. 0 and 0, since it mentions that there's no acid or hydroxide originally. Our change is going to be X, X, and X. So at equilibrium, we'll have 0.30 minus X, X, and X. Now we'll plug that into our K expression. 1.39 times 10 to the minus 11 equals X squared over 0.30 minus X. We'll assume that our X is insignificant, multiply both sides by 0.30, and take the square root of both sides to solve for X. So X equals 2.04 times 10 to the minus 6. And we want to do our 5% rule to prove that. So we've got 2.04 times 10 to the minus 6 divided by 0.30 times 100, and we get 0.00068. So we're good with that 5% assumption. Now we want to calculate the pH of the solution. We have to remember that X equals our hydroxide ion concentration. So our pOH will equal the negative log of 2.04 times 10 to the minus 6, which will give us 5.69. So our pH will equal 14 minus 5.69, which gives us 8.31. And we said that sodium fluoride is a basic solution. Our pH is greater than 7, so that works out. Salts that produce acidic solutions. Some salts produce acidic solutions in water. It's usually salts in which the anion is not a base and the cation is the conjugate acid of a weak base. So a good example of this is sodium or ammonium chloride. If we take ammonium chloride and dissolve it in water, we know that it's soluble from our solubility rules. We're going to produce ammonium ions and chloride ions. Now chloride is the anion of hydrochloric acid, which is a strong acid. So chloride has no affinity for hydrogen ions. But ammonium is the conjugate acid of a weak base. So that ammonium ion will dissociate into ammonia and hydrogen ions. Since we're producing hydrogen ions, we're looking at an acidic solution. So we have another example. We want to calculate the pH of a 0.10 molar ammonium chloride solution, and it gives us our Kb value. So we have our ammonium chloride, which will break up into ammonia ions and chloride ions. And we know that we're going to be dealing with the ammonium ions. So the ammonium ions are going to dissociate into ammonia and hydrogen ions. So we're given a Kb, but because it's an acid, we need Ka. So we've got Ka times Kb equals 1.00 times 10 to the minus 14. So X times 1.8 times 10 to the minus 5 equals 1.00 times 10 to the minus 14. So Ka equals 5.6 times 10 to the minus 10. Now we'll make our ice chart. So we've got ammonium, ammonia, and hydrogen. Initially, our concentration of ammonium ions is 0.10, since our salt 100% dissociates. We've got no ammonia and no hydrogen. It's a weak acid, so X amount of it will dissociate. So at equilibrium, we'll have 0.10 minus X, X, and X. We've got our Ka expression, which will be ammonia times hydrogen over ammonium. So we've got 5.6 times 10 to the minus 10 will equal X squared over 0.10 minus X. We'll assume X is insignificant, multiply both sides by 0.10 and take the square root. That'll give us X equals 7.5 times 10 to the minus 6, and that's our hydrogen ion concentration. We'll do our 5% rule. So we've got 7.5 times 10 to the minus 6 divided by 0.10 times 100, and we get 0.0075. So X is insignificant. We're good with that. And since X is our hydrogen ion concentration, if we take the negative log, that'll give us our pH. So the negative log of 7.5 times 10 to the minus 6 gives us a pH of 5.13. And we said that our solution was an acidic salt. Our pH is less than 7, so we know that we're on the right side of our pH scale. So salts are electrolytes that are not acids and not bases. They have something other than hydrogen as their positive ion, something other than hydroxide as their negative ion. When they dissolve in water, they're either going to be characterized as neutral, acidic, or basic, depending on what the ions are that are produced when that salt dissolves. If the ion has an affinity for hydrogen ions, then we're looking at a basic salt. If the ions give off hydrogen ions, then we're looking at an acidic salt.